All right, welcome to The Explainer. Today we're diving into something that really pushes the limits of what we think is possible. We're talking about the physics of so-called impossible flight. And this isn't just sci-fi stuff. This is based on real data from some truly mind-boggling encounters. Now, you might think that quote is pulled straight out of a science fiction book, right? Nope. That's from a real, peer-reviewed scientific paper. And what they're looking at is declassified military encounters. The two phrases that should jump out at you are structured craft and impossible flight characteristics. That combination right there, well, it sets us up for a genuine, data-backed mystery that we just have to dig into. Okay, so impossible. How impossible are we talking about here? Well, check out this number, 5,370 Gs. That's the estimated acceleration of the now famous Tic Tac UAP from the USS Nimitz encounter back in 2004. Let's try to wrap our heads around that. 5,370 times the force of gravity. Any plane we've ever built would be turned into confetti instantly. And a human pilot? Forget about it. It's just completely beyond anything we can survive. So yeah, what exactly makes these things seem so impossible? Let's break down the key characteristics that keep getting reported over and over again. And remember, we're talking about reports from highly trained pilots and sensor operators, often with multiple systems confirming what they're seeing. When you actually lay it out like this, side by side, it's just incredible. Look at the performance gap. It's not even a gap, it's a canyon. Take sudden acceleration, for example. Our absolute best fighter jets, like the F-18, top out around 7.5 Gs before the plane or the pilot starts to have a really bad day. These things, they're clocked at hundreds, even thousands of Gs. You know, this isn't just a slight improvement. It's like they're playing a completely different sport with a totally different set of rules for physics. All right, so that brings up the big question, right? Why can't we do this? Why can't we just, build a ship with some super powerful magnets, push against the Earth's magnetic field, and float away? Sounds simple enough? Well, there's a huge wall in our way, and it's a wall called physics, specifically a rule that's been on the books for almost 200 years. And here it is, Earnshaw's theorem. This thing was proven way back in 1842, and it's basically the ultimate buzzkill for anyone hoping to build a simple anti-gravity machine. What it says, in a nutshell, is that you just can't get a stable, floating object using only static magnets. It's impossible. There's always going to be a direction where it's unstable. This is a perfect way to think about it. It's exactly like trying to balance a pencil perfectly on its tip. You can try all day, but even the tiniest nudge, a slight breeze, and it's over. It falls. It's the exact same principle for magnets. Earnshaw's theorem is that nudge. It guarantees there's always a way to fall. So just using static magnetic fields for levitation, yeah, that's pretty much a non-starter. Okay, so if we can't just push against gravity, what if we cheat? Is there a loophole? Could we maybe bend the rules? Instead of breaking through the wall of physics, what if we could just warp the space around the wall? Now we're getting into some seriously weird territory. We're leaving behind what we know how to build and jumping headfirst into theoretical physics. And this is where things get really interesting. We're talking about concepts straight out of Star Trek. But here's the kicker. They have a real basis in mathematics, specifically in Einstein's theory of general relativity. So, meet the Alcubierre drive. This is a wild idea proposed back in '94. The concept is that you create this warp bubble. You squish space-time in front of you and stretch it out behind you. The craziest part? The ship inside the bubble isn't moving at all. It's basically surfing on a wave of space-time. And because you're moving space itself, not moving through space, you can technically go faster than light. It's an absolutely brilliant idea, but yeah, there's always a catch, and this one is a big one. So what's the catch? To make this warp bubble work, you need something called negative mass. And no, that's not antimatter. It's something way weirder. It's a theoretical type of matter that has, well, negative mass. It wouldn't just be unaffected by gravity, it would be gravitationally repulsive. It would literally push space away from it. This is the key ingredient, the ultimate anti-gravity stuff. And it gets even stranger. I mean, just look at these properties. They're completely bonkers. So a regular positive mass would actually pull a negative mass towards it, but the negative mass would push the positive mass away. Think about that for a second. The result is this thing called runaway motion, where they would just chase each other, accelerating forever without any new energy being put in. It sounds like it breaks the laws of physics, and it totally messes with your intuition. And of course, the big caveat, nobody has ever found a shred of this stuff. It's purely on the blackboard for now.
All right, let's pump the brakes on rewriting physics for a second. That's a huge mountain to climb. So let's ask a different question. What if we don't need new physics? What if we could just be really, really clever engineers? Could we maybe piece together existing or near future tech to fake it, to mimic the kinds of things we're seeing?
So here's one possible blueprint for how that might work. It's a bit of a kitchen sink approach, combining a few different advanced ideas. First, you start with a classic saucer shape. Why? Because it's actually pretty good at generating aerodynamic lift. Second, instead of jet engines, you'd have an ion lift system. This would zap the air around the craft, turning it into ions, and then use an electric field to shoot those ions down. That gives you silent thrust, no moving parts. Third, for steering, you'd use something that's still theoretical but really cool: magnetic monopoles. Basically, a magnet with only a north or a south pole. You could use those to push and pull against a planet's magnetic field. And to power this whole beast, you'd need a ton of juice, so you'd have a compact nuclear reactor on board. Now, is this real? No, but it's all based on engineering concepts we can at least wrap our heads around. So really, when you boil it all down, we've got two different paths to get to this impossible flight. You've got the physicist's path, which is all about a total revolution, finding something like negative mass that completely rewrites the rulebook. Then you have the engineer's path. This one isn't about rewriting the rules, it's about mastering them, using a clever combination of advanced tech to create the illusion of impossible flight. So, revolution versus evolution. So, after all that, what does it all mean? Where do we stand? Well, looking at this stuff, this impossible propulsion, it really forces us to stare right at the edge of what we know. It makes us ask, what's next? What's just over that horizon of understanding? And it doesn't really matter which path is the right one. Whether these sightings are a glimpse of a technology we just haven't built yet, or evidence of a physics we don't even understand, either way, it tells us something really important. There are still huge, profound mysteries out there. And that gap, that space between what we observe and what we can explain, that's exactly where all the exciting discoveries happen. Which leaves us with the biggest question of all, doesn't it? Are these impossible technologies a sneak peek into our own future, a roadmap for what humanity could one day achieve? Or are they proof that we're not the only ones who have figured this stuff out? And that question, really, is what makes this all so captivating. It's not just about cool machines. It's about who we are, where we're going, and what our place in this universe truly is.